Greetings and welcome once again to my new calculus channel. My name is John Gabriel, and today I have an interesting video for you on Descartes, who happens to be my favorite French mathematician, and I believe he was certainly a very smart guy. And having said that, I don't think he fully understood the concept of number because he never defined it anywhere, as I have. So let me start with his first, or with his major publication, which is called La Geometrie. So in his work, he talks about something in his first book called extraction of the root, the square root. So also, if you happen to read his book, you'll see that nowhere does he actually set out a method for finding the arithmetic operations between the different magnitudes. So for example, he's got this diagram here which shows you how to do multiplication in arithmetic, but nowhere did he say, first of all, what is number, and second of all, how to do the operations of arithmetic without number. And the only place that you will find such a publication is here on LinkedIn, and it's free. I show you for the first time in human history how the ancient Greeks performed arithmetic without numbers and how you got your arithmetic, because this here is the way algebra imitates geometry with an abstract unit, and why algebra is not 100% precise or exact. In fact, in most cases, arithmetic with algebra is not 100% correct, because it uses something called the abstract unit. And I don't think that Descartes actually understood it this way, although he had a pretty good idea, because he says here, for example, let A be taken as unity. So it seems that in geometry he understood you could choose any unit. But it seems that he didn't quite understand from this paragraph. But I may be wrong, actually. I mean, I'm not Descartes, and I didn't live in his time. So it's possible that he did have an understanding pretty close to mine. But anyhow, he never defined unit, and he never showed in any of his books how to do arithmetic without numbers. I am the only one to do that. And I want to stress that because it's a very big accomplishment, okay? And a lot of people don't realize how big this accomplishment is. So, in a previous video, I showed you how to do the four operations. I gave you a circle like this, and I explained to you that, for example, these three magnitudes, the magenta, the blue, and the red, are actually expressed with relation to the green line segment. Okay, the green line segment is in fact how they are all related, because the green line segment measures all of them. So if I had to tell you that the product of the magenta to green ratio and the blue to green ratio is the red to the green ratio, it looks exactly like that. That's what this means. This is a true statement in geometry, and there's nothing else to be done here in geometry. Okay, so where does algebra differ with this? Well, algebra takes this a step further. It takes the measure, which means it condenses that into a number, okay, and that, okay. So it condenses these into numbers, and I'll show you how that happens. So for example, in this diagram, I think in this demonstration that I've showed you many times, algebra does this, okay? It measures this line segment with the green one. So if you take the green line segment, so for example, if I had to say, take a segment with given length, go like that and say 1, okay, and then I could use that. I don't know why I'm not able to move that. I should be able to move that. I could go 1, 2, and 3 exactly, okay? And on this side is just exactly 1. So it's a measure, okay? That's what I meant often when I talk about pilikotita or quotientness, which even the stupid mainstream Greek morons of today don't understand. Okay, but that's what it means. That's what quotientness means. It means you can take, it means that the ratio you're using, for example, inside here, means that any of these ratios have a common divisor. That's what it means. That's all it means. So it means this, 1, 2, whatever, this, 1, 2, 3, etc., and the result. So in geometry, that is what happens. But in algebra, we take the measure, which is 1 in this case, and let's say, I haven't drawn these ratios to scale, so it's not going to look right. But the exact problem is shown here. Okay, it's shown there. So you just go there and you look at that, and you can do it with any ratio you like, and you say 1 times 3, it's going to equal to 3. Okay, so this is called algebra. This is called algebra. Okay, and I go a lot further than this. I show you how to do this with fractions. That's right. I happen to be a genius, and I think that if Descartes knew about these things, he would have written about them. Okay, so he didn't know about these things, in my opinion, and that's why I didn't write about them. But he knew a hell of a lot, and he was instrumental in bringing ancient Greek mathematics to the stupid masses of humanity. Okay, in other words, without Descartes, we wouldn't have been where we are today. So he was a great mathematician, the best French mathematician, in my opinion. And so I only have good things to say about him. That's Descartes for you. Now, let's look at his extraction of the root, because this is what my video was meant to be about. So in his extraction of the root, he says, just draw a semicircle. Well, first of all, draw an antecedent, this line segment, SD, then the consequent SS. Then find the midpoint, which is the center. Very easy to do all geometrically. Draw a semicircle here with diameter SD plus SS, and draw it perpendicular to this colon, okay, which is this point here, all right, perpendicular. So draw the semicircle perpendicular. Draw this SR perpendicular to the diameter, which is the addition of those two. So the proof is not difficult. If you look at the proof, you don't really need the first line. I just put the first line in for information. But if you take the magenta hypotenuse and the orange or hypotenuse and you add them, you'll end up with this identity here, and you'll end up with SR squared is equal to SS times SD, or you'll end up with the fact that SR is the square root of this. Okay, and by the way, it doesn't matter whether this here is 1 or anything else. This is always the square root of that. How? Well, consider that if you take different measures like this. Okay, now let's change that. That's 2 now, okay? So now this distance here isn't really 3 as far as geometry is concerned. So its actual distance is, as far as algebra is concerned, it's 3 divided by 2. It's actually 1.5 in algebra. So how do I get that? All right, well, let's go to ratio measures. So let's move that out of the way. So you see over here, the measure of SD by SS is 1.5. Okay, and also the measure of SR by SR is 1.22474, which is the square root of 1.5. Okay, so if you say 1.5, hang on a second, 1.5 square root, that's what you get, 1.22474. So Descartes appeared not to realize that this doesn't have to be an algebraic unit. It can be anything in geometry, okay? In other words, the geometry says that if you have a semicircle, then these two parts are going to be equal, this part on top here. So if you connect this like that, then the product of this line and this line is always going to be this line, because everything is expressed in terms of this unit, okay? Does that make sense? Yes, of course it does. So you have to think about this very carefully. It's not easy to catch. So what I'm saying is that if SS equals to 1 and SD is a multiple of 1, then the above here is easy to see because algebra treats every ratio measure in terms of the abstract unit, like I showed you here. Okay? Get it? Okay. Then geometric arithmetic applies magnitudinal unit measure to any pair of ratios of magnitudes, also like I showed you here. Okay, magnitudinal. This here is the result in geometry. Okay, that's the result. To get the result in algebra, you have to measure the parts of this ratio, make sure that they have a common divisor, and then using a simple count, which you assume to be the unit, the abstract unit, which is this green line by itself, then two of these green lines, It's not circular because if you take two of these green lines, you can do this and just say that, oops, I didn't mean to do that, and just grab that and put it down here, and you can get another one like that. And so, I hate it when that happens. Let's get that. So add these up like this, or just put them together, and then define two. Well, one would just be one of these green lines to itself, right? It would be one of the green lines to itself. So two would be two of the green lines to itself. So you have counting in place before you actually enumerate the parts of this ratio or these ratios in algebra, meaning you are actually performing measure. So as the great John Gabriel has taught you, a number is a name. Like I show you here, for example, is a name. 2 is equal to the measure of this ratio. Okay, it's a name given to the ratio. So there's nothing circular, and you'll see that in my one-page realization of number, which will also be in the detail section. This stuff is important. That's why I cover it. Okay, so pay attention. Then you can see that geometric arithmetic applies magnitudinal unit measure to any pair of ratios of magnitudes. And Descartes did not necessarily understand arithmetic without numbers, although a lot of what he wrote indicated he had a pretty good idea. And so this theorem that he has here is unremarkable, because if you look at it in let's do this, let's do that, and then bring that down to 1 like that. I'll try and make them 1, actually. Make this 1 as well. So if they're equal, if these two lines are equal and you move them anywhere along here, right? Anywhere along here. So if you draw a line there, then this is equal to this. So always this line times this line will be this line if the magenta line is assumed as the unit. Okay, it doesn't have to be 1, by the way. It doesn't have to be 1. It can be anything. Hide these measures. It can be anything. Okay? Doesn't have to be there. It can be there even, as long as these two, the green is equal to the red and the magenta is taken as unit. All right. So it's a pretty interesting understanding if you get what I'm saying here. And here comes the crux of it. The theorem is unremarkable, or the extraction or the method is unremarkable, since it is a consequence of arithmetic without numbers. This article here, by the way, okay, explains everything to you. And even better, my free ebook, Learning the Correct Way. This book here, by the way. And you can get it with the watermark on Academia if you create an account and log in, or you can get it without a watermark on Amazon Kindle. And so It's unremarkable because it is a consequence of arithmetic without numbers. In geometry, there is no such thing as the square root of 2. Okay, no such thing. The square root of 2 is 100% algebraic. And math academics confused the failed measure of the ratio of magnitudes diagonal to side with a perceived construction of the number. You can't construct number, you idiots. It's not possible to construct numbers, okay? That's just nonsense. Whenever somebody says that, I cringe. Please don't say something stupid like that. You cannot construct a number. So if you have a square like this, I think this is a square, and you try to measure this diagonal, this guy here, this diagonal, okay? Get a pencil. You try to measure this with either of these equal sides, okay? With either of these equal sides, you'll get something that comes close to this, or more digits if you care to find them, okay? It's not important because there is no such thing as square root of 2, or this thing that you see here in algebra is treated as a number, but it's not a number, okay? It's treated as a number, but it's not a number. And when you say, oh, yeah, but if you square it, it's equal to 2, which is a number. Yes, that's true. But the operation of squaring doesn't do anything to what appears under the radical. I mean, you can have idiot, for example, like that, squared. And that will give you, that's right, idiot, which is what most of you are. So, yes, square root 2 is not a number. Okay, that's pretty important, and that's something that Descartes didn't understand, I think. And so math academics often confuse the failed measure of the ratio of magnitudes with a perceived construction. Please don't say you can construct number. There's no such thing. You cannot construct number. In geometry, you deal only with ratios of magnitudes, homogeneous magnitudes. They can be line segments, they can be areas, they can be volumes. They're never numbers, okay? So, to learn much more, you have to study my articles to become a genius like me. And don't waste any more time. Become a subscriber to my channel. This is the new calculus channel. Click like on my videos and follow me on Academia.edu. This is where I sometimes share priceless information, like this book and many other articles that I've shared with you. Okay, ancient Greek trigonometric formulas. There is so much here for you to understand. This is also an important article. It's the realization and development of number in one page. I give you all these links in the details section every time I post a video to my YouTube. I'm John Gabriel, and this is the new calculus channel. Till next time, goodbye.